All right, so this is the first time we're organizing this event, and so I'm going to tell you the story of how we came to be here, but hopefully it's exciting for you. And we're recording this so we are able to share this with others, and hope you find it useful for whatever you're working on. And hopefully later on you also have a chance to tell us a bit about yourself and why you're interested in this, but let's just get started for now. So me and Jose here, so we both are organizing this event. Feel free to ask questions. So yeah, so I'm based here. So I'm a research scientist at CCEL. I'm a part of the computer assisted group at MIT, and Jose graduated from here as well. You were with Martin, right? Martin Reynard. And now he's with Microsoft in the pros team. So yeah, so we have a couple of sponsors for this event. So first is the National Science Foundation with this project on neurosymbolic learning. So feel free to check out that website, since that's the starting point where we were able to host this, because this project was funded. And we are grateful for the NSF for giving us some grant to start this research. And also Google for Education provided some funding some time ago. So I'm also grateful for them. So they were able to provide some lunch for you guys. So yeah, so first I wanted to give you a background on, on what's happening in AI. And I decided to put this story on ChatGPT because it's everywhere. And so this is actually from the New York Times. So if you go to the New York Times website and you search for ChatGPT, these are the stories that you're going to find. And it's funny for me how this is becoming such a mainstream topic to talk about, because it seems that it's affecting everything. So we have people worry about, hijacking democracy, if this is going to be is going to take jobs from someone else, or if you're going to be unemployed for ChatGPT. So it's very interesting for me to see all these stories. And yeah, so I just wanted to know, are all of you aware of ChatGPT, or some of you have never heard of ChatGPT? Who has never heard of ChatGPT? Great. So, all right. So I'm glad that you guys know about this. So I also like this comic, which kind of like summarizes what ChatGPT is. So you have these two people in there, and one asks the other, so this is your machine learning system. Yes, you pour the data into this big pile of linear algebra and collect the answers from the other side. And then what if the answers are wrong? Just steer the panel until they start looking right. Right, so summarizing, this is what is ChatGPT and these large language models, right? So the point I wanted to make here is that it is quite a mystery still to know how these systems work, right? So we're able to train them, and we're able to find architectures that work. But at the end of the day, systems like ChatGPT, we still don't know what is the principle that makes these systems work, right? From the science perspective, which is why we're here, right? So for me, I think ChatGPT is more of an engineering impressive effort. And I think that there is still too much to know on how that system works. So, behind that is also this deep learning revolution, which, I still remember in 2014, where these systems were just taking off in the Google, and we had these first libraries like Caffe, and the first version of TensorFlow, and we had at that point Theano. So it's very old days of deep learning. And so yes, it's really impressive where we are today, right? So I never imagined. So yeah, so in 2014 I was working on my PhD, and I decided to apply these techniques to the problem I was working on, which is related to gait walking. And it was a novel idea to try, but not nowadays, right? Nowadays, everyone is using deep learning, and it's very easy to apply, right? So we have all these libraries, PyTorch, TensorFlow, and then we also have applications on small devices, right? Low energy, low consumption. So for me, it's really impressive how the adoption of these techniques have been, and at the end of the day, I just wanted to put these 3 points, which kind of like summarizes the techniques, which is, you have parameters that can be differentiable. We can minimize the training loss based on this gradient descent approach. And, as I said, there is a mature software ecosystem, right? So I think this is the reason why we have such an adoption today, right? So also, I wanted to talk a little bit about the transformers. So ChatGPT is based on this transformer architecture, and it's interesting if you read the main paper, which is attention all you need. This is paper a couple of years ago. I don't think the authors really realize the impact that this architecture had, even themselves, right? Because you just read the paper, they never claim anything that that is actually the papers that claim that they're going to change the world, they never do. And this paper just was claiming like a language translation claim, right? That they could do it better than other systems, but like the effect that it had is quite impressive. And just based on an encoder and decoder architecture. And then we have these embeddings and this input, and this is kind of like an abstraction, right? Because at the end of the day, we have something as complex as this, right? So it's quite interesting that, if you have heard of ImageNet, which is this very first data set that was created for AI, right? So to be able to scale the AI, and where we find the first deep neural network paper. I think that the ImageNet architecture just came up to ResNet, which is this residual learning. And then we have something like this, right? Which is really complex and many layers, and we have this encoder and decoders. And yeah, I think it's also interesting to me why this very specific architecture, right, is the one that is really taking over AI today. But so I think Jose will be the person that will be doing something with large language models. So I think Jose will be playing with these models a little bit later, and hopefully you also can get some hands on there. So, well, I also wanted to ask, who recognizes this image there? Have you ever seen this? No, no one has a guess. Yeah, exactly. So that's a real implementation of a Turing machine and real world. So it's, I think I am very, I admire, I think Alan Turing a lot. So, I actually was in Manchester before doing my PhD, and, he was teaching there, and, the UK has this very, they respect him a lot. He has a lot of statues all around the country. But yeah, I think what he did really several years back, just proposing this Turing machine and like general computation, I think is quite a profound idea. And I think that a lot of us in computer science really are inspired by this. But just, it's kind of like the beginning of computer science, and how does this relate to a computer program, right? So basically, it's a description of how to perform a computation. And then also we have some syntax, some semantics, and so we have to design a language that has the right level of expressiveness, right? And we're going to be touching, this is a very brief intro of computer programming. We're going to see this later on in many of the tutorials, because this is a workshop based on programming languages, right, and AI. And for example, the next tutorial would touch on this specific techniques. So does any of you have a background in programming languages? Show of hands. AI? I think AI, you do, right? Okay, so we have mostly AI people here, but yeah, so we have this combination of programming languages and AI, and we're going to touch on these concepts later on as well. So, well, I think now that we have provided some background on, deep learning, what's a program, and I think now we can touch program synthesis, right? So here is another example of a very widely known tool, right, which is called GitHub Copilot. And do any of you use GitHub Copilot for your development? Show of hands. Just 2. Wow. You should use it, guys. It's very useful. So yeah, so what happens with Copilot is that you start typing your program, right? So suppose that you are trying to solve a problem, and sometimes just by giving Copilot the comments, right? For example, here you can see on line 15, it says take an array, flatten it, and check that the depth is 0. Just by writing that and then writing a function, something, then it will try to pop up the rest of the program, right? Based on what you wrote before. And it's actually very useful. So people say that they save them time like 30% in like programming. Right, so this is one form of program generation because it's generating code, right? So the part that you see down there, down on line 16, is something that the system is generating, right? So based on the previous code and also on where, what kind of things are you asking the system to do? So I think it's pretty interesting. So Jose, are you going to do a demo on Copilot or not? No. Okay. Okay. Yeah, because well, it's open to anyone. Right? Yeah, so you can just sign up, and I definitely encourage you to use it. I think it's a very productive tool, and yeah. So this is a form of program synthesis, right? And then in the more traditional, terms, we have computation. Then we're trying to, pass this.
I don't want rain.
And then at the end of the
below 50 really.
Okay. All right, so we have this specification, right? That's something that we want to do, right? And the goal of program synthesis is that you use that specification, then just pass it through a system that will just, work with the specification. And then at the end, you generate the code, right? So these are the 3 main steps, right? So instead of you writing the code yourself, right, you just give the system a specification, then just pass it through this pipeline, and then you will get some code at the end, right? So this is the main idea of program synthesis. And for example, to be more concrete, you can give something like logic, just as a specification, and then you can use deductive synthesis or some kind of system that uses some kind of form of search, and then you can generate, for example, C code and proof of what you want from these specifications. And more generally, these are the kind of inputs that you can have, right? So you can have like input-output examples, as we saw before, logical specifications, natural language, right? So I think, for example, ChatGPT can take natural language. That's an example of natural language. And then in the system itself needs to have these properties, right? It needs to have some grammar, DSL, like a domain-specific language, components, right? And at the end of the day, we want to find a program, right? So this is very briefly what we're trying to search for. And so this is kind of like the dimensions of program synthesis. And if you work in the space, you could see that these are the main components, right? What this field depends on, right? So first of all, we need to specify the intent, right? What do you want at the end, right? What is the actual thing that you want to accomplish, and how can we get there more efficiently, right? And then we have search space, right? So in our case, we're searching over programmatic space. So we have all these different types of programs that could be a good candidate to solve the solution, to solve the problem that you have, right? And then we can have different types of strategies as well, right, on how to arrive to that solution. But these are the three things that, as a program synthesis computer scientist, you need to balance and to understand and to really work on in any of your research projects. So now, you have some kind of background on AI, machine learning, deep learning, and also on program synthesis, right? And the idea of our project, or the Neurosymbolic project I showed you at the beginning, is to really blend these two approaches, right? So on the one side, we have deep learning, and the other side, we have program synthesis. And our research in our lab tries to see how those two could interact, right? And how can we make more powerful systems based on this idea that maybe these two techniques could complement each other. So if I move on, do you have any questions so far? Or? So yeah, in one side, we have the two approaches we already talked before, right? So in our case, when we talk about program synthesis, we refer that to a symbolic program, right? So it's the same. So don't think this is a very different thing, but a symbolic program for us is a synthesized code from a program synthesis approach that we have. I mentioned before the types, right? So the benefit of that is that it's interpretable, right? You can verify it, and then you can also have structural domain knowledge. Right? And on top of that is data efficient, right? So these are kind of like the four benefits of having something like a program synthesis to be able to attack a problem. And then on the other side, we have neural networks, which can scale and be flexible and also can handle messy data. But I think that they are very easy to get started with, right? So as I said before, we have a huge ecosystem of libraries, and people are all the time developing code here and putting it on GitHub. So I think we have many more projects on neural networks than in program synthesis, right? But these are the two things that are kind of important on each of those, and our goal is to try to bridge them, right? So how can we use the benefits of both the program synthesis approach and the neural networks approach and try to build neurosymbolic programs combining these two techniques. So more specifically, so this is the technical overview, right? So, but also we want to apply this in science, right? So going beyond the technical details of like how program synthesis work or how deep learning works and how each of them can complement each other. At the core, we have this question, how can we apply these techniques to the scientific process, right? So here, the image that you can see here, it's from a paper we published recently, and Megan is here, so you can ask her as well if you have questions. But so we published this a couple of months ago, and it's just a perspective project on how we think these techniques could impact science, right? And as you can see here, we have the scientific process on one side, which we start with a research question. We generate a hypothesis, we have the experimental setup, we do the analysis, the interpretation, then we report to the community, right? And I'm not going to go into detail in each of the sections here, but you're welcome to read the paper. And we make the connections there, right? So most of the people in our team have very strong, computer science background, right? And some others have very strong application background, right? So what we're trying to do in this project is try to mix these two and try to do some interesting, to find some interesting insights in the context of science. And these this paper makes the case for this, like how we can apply these techniques for science. Happy to chat also offline if you want to know more, but the paper is there to explain more. So another way to frame the interpretability, and that actually connects with something that you are probably familiarized, is with some of these equations, right? So the reason why we want to find this code is because in science, is because this code represents some of the equations that you find, right? So the idea is that, you know, these the discoveries of these things go all the way back to the 1600s, right? When Newton first proposed calculus, or even before, right, with the Pythagoras theorem. So all of this is just, you know, trial and error, right? So actually the pioneers that thought about calculus and how to express a model of a word in math and just, you know, this equational form is quite a very achievement, right, for humanity. I think a very big achievement for us to think of the world this way, in this simplified way. But the idea that we have is in this project is, can we arrive to something like this from data, right? So at the end of the day, we depend on data, on experiments. And the idea is to use this neural network learning, parameter synthesis, and come up with something like this, right? Based on a learning algorithm and some kind of data you have of a problem. And, you know, so we're going to touch on this during the tutorials, and we have Miles coming a little bit later, which is going to be like a physics-oriented problem. And you're going to see exactly how can we arrive to something like this with the techniques I just mentioned. But the main idea is this one, right? So how can we arrive to this form of equations from data and from the techniques that I mentioned before? So, you know, so the programs have also all these benefits, right? So we can have executability, right? So it can be evaluated in silico how certain experiment behaves. We can have interventions, right? So you can also modify what you find, right? So for example, in the equation that I showed you before, what happens if you drop a term? What happens if you add a constant, right? So all these interventions is quite powerful, right? And this connects with causality, right? So any of you are working on causality? Yeah. So this connects to causality, right? So if you are, which is another area of machine learning that's very active nowadays, it's how we can just, you know, modify a system and really see the effect of intervention in that system, and do it just, you know, computationally, right, without going out there and seeing the world, which just, you know, has huge implications, right? If you could do this in computational terms, you know, you could save a lot of money in healthcare and all these people that are trying all these different drugs. And just to mention one example, right? But there are many others. And so we also have modularity, right? So we can break this up in several parts, right? Understanding how each part behave. And as I said, I think the most important part is the interpretable aspect, right? Instead of having this big pile of linear algebra, as I mentioned before, so we have something that can actually read and understand as humans. And we are hopefully that just, you know, we can find those type of programs in the context of science. So here is just, you know, side to side, just, you know, how programming languages, just, you know, and machine learning complement each other. So in one side we have formal reasoning, modularity, data abstraction, and the other side we have neural architecture, optimization, and uncertainty, right? So which we already have discussed this. So so this is an actual pipeline, right? So I think we've been a little bit high level, but this is just, you know, in order for you to understand a bit better of what we mean with, you know, symbolic programs, you can see that this is actually how we intend that to be, right? So in one side you have the data, you have the programming language, right? The DSL, the domain specific language. Then you add some constraints to the problem, right? So you have, can be safety, robustness, and in other cases, you cannot break the laws of nature, right? So for example, if you can have some ranges, right? Or temperature cannot reach more than a certain value, or cannot go beyond below a certain value, right? So all of those constraints that we know that exist in nature, you can incorporate them here. And also the next tutorial with molecular discovery, we're going to talk about that as well, like how the properties of chemical elements limit your system, right? And next speaker will go a little bit more on that. And then at the end of the day, we have this neurosymbolic program where you have a mix of neural networks and symbolic code. And just, as I said, you can see that you have your X and your Y, which is how machine learning systems work. You have your input and your output, but in the middle, you don't only have neural networks, but you also have some computer code. So here are also the different ways that you can mix these two techniques, right? So this is from a survey paper that my team wrote last year, and I'm going to show you later the reference, and you can look at that. But this is how we are looking at the problem, right? So how can you mix these two components? What does it mean to mix a symbolic component, a neural network component, and a mix of the two? So for example, one of the recent projects in our lab is the component discovery goal, right? So how can you find primitives that could help you solve a problem, right? So when you have a domain specific language, it's very hard to really limit your problem, right? So what kind of primitives can you have to solve that specific problem? And here in component discovery, you find that automatically, right, from the data. So you don't have to worry about that much. And for example, that's one application of where we can mix these two techniques. And we're going to go over some of these during the rest of the workshop. So this is the actual technical paper. So you're also welcome to read it. And it's a survey, and it was published, as I said, last year. And all of the authors there, they're our colleagues, and they're part of the project that I mentioned at the beginning. So, if you want to really dig into the technical part, I would really advise you to read this survey. So, okay, so now going to the day, right? So we're going to have 4 main workshops, and we'll start with chemistry with Minga, which is here. Then we're going to go with maths, which is, he's in an interview right now, but he will be after lunch here. Then we have Jose, which will be tomorrow morning in code repair. And then Shashank, which will be also doing he's not here, but he will be doing the neuroscience. And just to give you a small preview of what's going to happen, right? So for just the workshop that is coming up right now, it's just a molecule-oriented workshop where we have some kind of input of molecules, and then we have a generative model, and then we want to generate more molecules, right? So we're going to learn how to do that, and this is an application of neurosymbolic programming, right? So you will see how Minga translated this molecular problem into a differentiable problem, and then how that differentiable problem helped him to generate more molecules, which is very important in chemistry because it's an expensive process to do it by hand. But Minga would go over this just after I'm done. So then the physics project, which is Miles project, we based on symbolic regression, and this will be connected to the ideas I showed before on physics, right? So the idea of this library, so he developed a PySer, which is Python symbolic regression, and is also on a Julia backend, and you can try it out. You can just go to the GitHub repo, but basically what we're doing here is to have some kind of symbols right? So in our case, this is like a more simplified version of program synthesis, right? Instead of having all this complex program, we only have a small set of symbols, right? We don't have a DSL in this case, but we have a data set and we have this genetic algorithm that will search over a model that will solve your data problem. And I'm really excited for this tutorial because it's, I think it will be very applied to many of your projects. So if you're working on something like this, it will be really useful for you to learn about the techniques. And yeah, so as I say, the tool is very robust and it's open source, so you can check it out. But this will be after lunch. And then we have Jose, which is gonna talk about program repair tomorrow morning. And just basically what it is just, you know, we all develop code, right? And we all have errors, right? Like, I mean, I've never heard of someone that develops code that doesn't have errors, right? So the idea here is how can we find these corruptions in code automatically, right? How can we go and fix it with an actual program, right? So a program, you know, like solving how you program and finding these errors. So Jose will be explain a bit more about that, and I believe it's a collaboration with OpenAI or.
We'll talk about different ways of approaching it, so we'll use some tools from OpenAI. A lot of the work also does is collaboration with both MSR and MSR.
Yeah, so this will be tomorrow morning, if you are interested in that. So this is more of a technical talk, right? So this will be more based on like actual computer science and how you repair any kind of code, right? Then the last tutorial will be based on neuroscience, right? How can we have this, how can we build models of understanding the brain, right? Suppose you have some neural data, right? How can we find models that find representations of neural data? Right, and the idea is that you can go back, right? So you can see the image on the left, upper left, right? So we have the code, right? Like some kind of Python code, and then you have the code model, and then the representation that you can find from that code. And the idea is just, you know, to go back, right? How can you change the actual source code based on things that you find in the neural representation in neuroscience, right? Because if you talk about neural representation, you might think of neural networks, right? But here in this case is like a neuroscience neural representation. Right? So yeah, so I'm really excited about this other application. This will be day 2. And yeah, so I just wanted to hear your opinions, right? So maybe start a little bit of discussion on if you have any other ideas on how we could accelerate science with computational models. Maybe you have something that you've been working on, or you have new ideas, or maybe you think that a purely deep learning approach will solve the problem, or you hate deep learning and you don't think that deep learning will ever find anything. So just wanted to hear from you if you have any ideas on your own research, on your own projects, or where do you think are the limits, right, of our understanding? If you think that science is such a manual process that you think will never be automated because it depends so much on human insight. So what do you guys think?
Yeah, I was thinking about summarizing something complex, see a lot of AI models do. Then I'll also think about, I can say I'm often when we ask better questions or scientific questions.
Yeah, so, you know, so something else I didn't touch on is another technique that actually in CSEL colleagues are working on, which is called probabilistic programming, right? And probabilistic programming is not much about program synthesis, but actually like a Bayesian approach to use, you know, scientific discovery, and also that's something that has been going for years, right? It has been too long since the first Bayesian models appear. But it's quite interesting that it's not widely used, right? And I always ask myself why techniques like those are still not like commonplace like deep learning. And sometimes also like computationally speaking is also hard to train these models, right? Because you are finding something called like a posterior, which depends on this Monte Carlo search, and no one has really found a way to optimize this and to make it fast. And sometimes just you have these limits, right, where you have like a very good technique, but it's not widely used because you have some compute limitations. So that's also something that to think about, right? That it is even if you have like a very good offer, it's if you don't have the means for people to make the jump easily or computational speed, right? They will not take off. But that's another none of the things that people have tried here, and that's still we're still waiting on like that breakthrough right moment where like deep learning where people will start adopting this more widely. All right, anyone else? Anything else you would like to mention? Yeah.
One thing I did that we have an intuitive sense of what we're looking for in scientific discovery, but until we like really define it, we usually don't realize that we actually want many things and we wait for them a certain way. And so I guess that would be something. So scientific discovery is to have a much clearer ideas that will also better guide what approaches we take. Because usually we take one approach, we can use different ones.
Yeah.
No one. Like so we want some book progression, but we won't be able to work with next data, for example.
Mm-hmm. You mean kind of like an hypothesis, like which ones do you pursue, or more like the actual experimental process that takes you to the answer?
More general sense about what we mean by scientific discovery. If it's an equation, then symbolic progression, but we usually in science want to be able to understand and work with the environment and better.
Okay. Yeah, no, I think you're right. All right, anyone on the Zoom room would like to say anything? I mean, it has been everyone very quiet there. Okay. All right, so as I said, this is the schedule for today. Thanks for joining. So now we move forward with the first workshop, which is Mingao, which is already here. And so we had summer school last year, and we're going to have one next year. So if you like what I showed you and the techniques that we're developing, feel free to join us next summer. And we also have seminars, so you can go to this website and join our mailing list. We host speakers that work on this area of research, so feel free to join us there. And yeah, keep in touch. And these are the other areas that this bigger project that I mentioned at the beginning is working on. So if you want to learn more, join us for the seminars. And thanks for joining. Any questions? Yeah.
I was thinking, okay, so the AI machine learning models better at the science.
Yeah, I mean, we are not saying that we're going to replace the human aspect, right? That will be, I think, impossible.
Yeah, that's the thing I guess I'm confused about. What exactly is that? Why is it?
Yeah, I mean, I think we'll never be able to get rid of the human, I think, because we always have a way to be involved, right? So I don't think we'll find a fully automated system that could really find things without human intervention. I think that's really far away, in my opinion. And I think that because, human intuition is, even when you work on these projects, right? So any of you that is working on AI or machine learning, you see how many details or how many problems, how many things appear when you're working on your projects, right? Like it requires a lot of human intuition, and a system that was able to automate all of that, I really feel that is really, really far-fetched. And we always need, I think, the human intervention somehow, right? Even like taking care of these systems. And for example, ChatGPT today, right? So it's actually surprising to me that it's actually not fully trained, right? This has a lot of human knowledge there. They hire a bunch of people in other countries, and they're like kind of like tuning the system, right? And so you can see there, right? Like even like something like a language model today, there really depends a lot of human intuition to fix these biases and to fix everything else that the system is not doing right. So even those models, right, that tend to be a state of the art, we depend so much on the human part.
Humans bring to the table that I don't often see in this line of work is in science. There's a very strong feedback between the theory and the experimental part. And for example, if you think of ChatGPT, basically we have this gigantic data set, given the data set, what is the best model that you can output. Whereas in physics, for example, you design the theory and then you think about how you're going to test that theory. Maybe it requires a new device, like the UHC, whatever that matter experiments, whatever set of complicated stuff to do, then you get some results back, and that feeds back into the theory. So it's a very, there's a very strong move where the human is crucial, that it's not often we don't think about automated science very close. Or well, rather program synthesis.
Yeah, I think it also is important to reflect in human history, right? We're just hypothesizing now, but we already lived so many things before, right? For example, the invention of the car, right? So, transportation is speaking, right? So we found a machine that can take us from point A to point B in a very efficient way. But still, right, we need mechanics, right? We need people fixing the cars, right? Do you think we can? That's the human element has never been away, right? It's always somewhere there, because it's always hard to manage all these inventions, right? Well, whenever a new invention arises, I think the human element just gets directed in a different way than it was before, but it's always there, right? At least that's the way I see it. Anyone else would like to add something to the discussion? All right, so then we'll follow with Miguel. Are you ready?